Pi molecular orbital theory of butadiene. The outline of presentation includes introduction to molecular orbital theory, structure of butadiene, overlap of p orbitals in butadiene, formation of pi molecular orbitals and energy levels, energy diagram of pi molecular orbital, delocalization and stability, applications of pi molecular orbital theory, summary. Introduction to molecular orbital theory describes the behavior of electrons in molecules using molecular orbitals formed by atomic orbitals. It explains bonding in conjugated systems like 1,3-butadiene using delocalized pi orbitals. Molecular formula of butadiene C4H6. Structure is CH2 double bond CH, single bond CH, double bond CH2. Contains 4 carbon atoms with sp2 hybridization, each having a perpendicular p orbital, atomic orbitals and overlap. Each of the 4 carbon atoms in butadiene contributes a p orbital that participates in pi bonding. These 4 p orbitals combine to form 4 molecular orbitals of increasing energy. Molecular orbital diagram of butadiene. So here it is Psi1, Psi2, Psi3 and Psi4. Psi1 will represent the bonding no nodes filled to electrons. Psi2 it will represent bonding one node filled to electrons. Psi3 star is anti-bonding 2 nodes, it is empty. Psi4 star anti-bonding 3 nodes empty. HOMO represents highest occupied molecular orbitals. LUMO represents lowest unoccupied molecular orbitals. Psi1 and Psi2 contribute to pi bonding, stabilizing the molecule. Psi3 and Psi4 are anti-bonding and remain empty in the ground state. The highest occupied molecular orbital is Psi2 and lowest unoccupied molecular orbital is Psi3. Psi1 lowest energy, fully bonding, no nodes, all p orbitals in phase. Psi2 bonding molecular orbitals, one node still bonding but less stable. Psi3 anti-bonding molecular orbital, 2 nodes higher energy. Psi4 highest energy, fully anti-bonding, 3 nodes least stable. Overlap of p orbitals in butadiene. Each carbon has a p orbital available for pi bonding. These orbitals overlap across the 4 carbon atoms, leading to a conjugated pi system. This overlap results in the formation of 4 pi molecular orbitals. The 4 p atomic orbitals combine to form 4 pi molecular orbitals. All p orbitals combine constructively, no nodes, that is Psi1, and 1 node is present, it is Psi2, 2 nodes appear, it is Psi3 in anti-bonding, and Psi4, 3 nodes. The molecular orbitals are arranged by increasing energy like Psi1, Psi2, Psi3 and Psi4. Electron filling. Butadiene has 4 pi electrons which occupy the 2 lowest energy bonding molecular orbitals, that is Psi1 and Psi2. The 4 molecular orbitals are arranged in increasing order only. Electron filling. Butadiene has 4 pi electrons and these electrons fill the 2 lowest energy molecular orbitals like Psi1 and Psi2, and Psi3 and Psi4 remain unoccupied in the ground state. Psi1 represents the lowest fully bonding, Psi2 will represent the partially bonding, Psi3 represents partially anti-bonding, and Psi4 is the highest fully anti-bonding. The delocalization and stability. The electrons are spread across all 4 carbons, stabilizing the molecule. Delocalization lowers energy and enhances stability compared to isolated double bonds. Applications of pi molecular orbital theory. UV visible spectroscopy. Pi to pi star transitions determine absorption properties. Diels order reaction. Reactivity influenced by HOMO and LUMO interactions. Chemical reactivity. Delocalized electrons impact reactivity patterns. Summary. Butadiene has a conjugated pi system with 4 pi molecular orbitals. Bonding and anti-bonding orbitals determine stability. Delocalization enhances stability and affects reactivity, used in spectroscopy and organic reactions. Thank you.